Hello, this is Dr. Viv. Let's look at a kinematics in one dimension problem involving vertical motion. I have two stones, one dropped from rest at a height h above the ground, and another stone that's thrown from the ground with an initial speed of v0. When and where do they meet? And draw some motion graphs. So this problem is a one-dimensional problem involving gravity. So we're going to assume that there is a uniform gravitational field indicated by the acceleration due to gravity vector g sub e, and that is given by the magnitude times the direction, which is negative j hat. The magnitude g sub e is 9.8 meters per second squared. And the minus sign means that it's pointing down. So if you want, you can draw a little figure to help you think about this problem. Here's the stone A. It's dropped, so the initial velocity is 0. And then it comes down. That's y equals 0, and that's y equals h. And then another stone VB, it's directly below, but I'm going to draw it like that. So VB equals V0. And at some point they're going to meet. Now there are two possibilities. They can either meet on the way up, or this can go up and then they can meet on the way down. We don't know which is the one that's going to happen. We'll derive conditions for the possibilities. But the mathematics will do all the thinking for us. So let's proceed to write the equations. The kinematical equation for the stone A is as follows. VA is VA0 plus acceleration times time. Well, the acceleration is just negative g sub e times time. The initial speed is 0, so that's just equal to negative g sub e times the time. For stone B, it's going to be v0 minus g sub e times t. Now in terms of the sign convention for velocity, let us agree that positive velocity is positive Vy is in the upward direction. The y-axis points like that. Let's also write the equations for the vertical displacement of the stone at any given time. So y sub a is going to be the initial y, which is the height, plus the initial velocity times the time, plus 1/2 gt squared. So that's going to be minus 1/2 g sub e t squared. Well, this term is 0 because the initial speed of stone A is 0. So I just have h minus 1/2 gt squared. What about stone B? For that, the initial height is 0, so I won't write it. Then the initial velocity is v0 t minus 1/2 gt squared. So those are the equations, and observe that the equations are they both have this acceleration term. So in a sense, you expect the acceleration not to influence things like the meeting time. I'll talk a little bit about that when we finish the problem. So let's write down the condition for meeting. The stones will meet when the distances ya and yb coincide. So let's set the equation for ya equal to the equation for yb. And the remark I made earlier proves true. The 1/2 gt squared simply cancels out, and this can be solved. I'll call this the critical time. The critical time is just the height divided by the velocity of the stone B. Now this can be thought about in a slightly dramatic fashion. Imagine that you're a filmmaker and you're trying to film this two-stone story, and what you do is you jump at the same time as the person drops the stone A. You jump with your camera. Well, then your camera is going to register the stone A as not being moving at all, because you are falling at the same acceleration as that stone. Meanwhile, the stone B simply comes up with constant speed, because the stone B, according to you, is not getting slowed down at all. Since you're falling with an acceleration g sub E, it somehow appears that stone B is simply drifting up with a speed v0, and indeed the time taken is the distance drifted divided by the speed of the stone. So this makes complete sense from that filmmaker perspective. The next thing we can do is to figure out where they meet. For that, all we have to do is put this critical time in one of those equations. We can do either one. So let me try doing both. The first equation gives me ya equals h minus 1/2 g sub e t critical squared. So I get h squared over v0 squared. And y sub b, if I used y sub b instead, I'm going to get v0 times the critical time, which is h upon v0, minus 1/2 g sub e, h squared over v0 squared. And here the v0s cancel out, and you can see that these two expressions actually agree. So we have found also where the collision occurs. Now the more interesting question is to decide if the collision occurs before or after stone B reaches the highest point. So the stone B reaches the highest point when its velocity is 0. So let's look at the condition that the velocity of stone B is equal to 0. That equation can be used, and I have Vb equals 0, and that gives me v0 minus g sub e times the maximum time. I'll call that the maximum time, Tm. This immediately gives me Tm equals v0 upon g sub e. And now I can find out the condition under which the stones meet before it reaches the highest point or after it reaches the highest point. So I'll substitute this t as g sub m in the equation for yb. So I'm going to get yb equals v0 times t sub m. So it's going to be v0 squared upon g sub e minus 1/2 v0 squared upon g sub e squared times g sub e. So I get v0 squared over g sub e minus half the same thing. So the answer is v0 squared over 2g sub e. So that's the maximum height of that stone. Okay, just save that. Now what we can do this kind of, so let's call this ybm. So one way to figure out if the collision occurs before or after is to look at ybm versus yb. And that's equivalent also to looking at the times. If the time t sub c is less than t sub m, then you know that it's on its way up. If t sub c is less than t sub m, it means the collision occurs on the way up. If T sub c is bigger than T sub m, it means the collision occurs on the way down. So that's another way of looking at it. Both ways can be done. I invite you to explore. So this is exercise for you. An exercise for you is to explore what happens when you set YB max is less than YB, YB critical. YB max less than YB critical means that the meeting the stone is it's gonna meet it on the way up. That's what it means. So let's look at a different condition, the time condition on time. The condition on time gives me it's on its way up if T sub c is less than T sub m. So let's look at the condition. H over V naught must be less than or equal to V naught over G sub E, and this gives me H is less than or equal to V naught squared over G sub E. Well, that's a very interesting condition because it tells you that it's less than half the maximum height. So if you start from less than half the maximum height, then you meet on the way up. All right, now finally let us, and I invite you to see that you get the same condition using this. Lastly, we have to draw the graphs, motion graphs. Motion graphs are sometimes really interesting to draw. In this example, we expect to see the velocity versus time graphs to be parallel lines because they have the same acceleration. Stone B is that, and I'm going to draw it for the case where it's meeting before the highest point is reached. Okay, so before the highest point is reached, the velocity of stone B is not yet 0. It's 0 when it reaches the highest point, but it's not yet 0, so it's some positive value still. It starts out with V naught and gradually decreases. Stone A starts from 0 and gradually increases its speed in a negative direction. So both of these graphs are pointing down. So that's the velocity versus time graph. Let's now draw the position versus time graph. Now, as you expect, you're going to get parabolas here. The story for stone A is that stone A would, this is stone B actually, B is the one that arcs up, and then stone A is simply thrown down. So I'm just drawing the dotted lines to indicate what does not happen, because when the stones do meet, that's the critical place, y sub c, and I'm drawing this for the case where y sub c is a little bit less than y sub m, so it's meeting on its way up. That's going to be your T sub c, and I'll indicate all the things I worked out in the problem. That's going to be your T sub m. Okay, so that gives you a good idea of how things are going to look. And this graph, drawing graphs like this is very helpful because it helps you see all the features of the algebra which are right there. And these algebraic equations are essentially either straight lines or parabolas, upside down because of the negative sign here. But in a nutshell, you can see how you can possibly get them to meet on the way down instead of the way up. So if I made this graph really small, then it'll meet on the way down, for example. So I again invite you to play around with all these things, put actual numbers. That'll be even more fun.